All right, so let's look at an example second order equation. All right, so we're given this equation and the initial condition that y of 0 is equal to 3 and the initial derivative is equal to 0. Okay. All right, and so in this case, it looks like my input is u of t. So remember, the input is always over on this side. X of t is my input. And that input is apparently a unit step, u of t, right? So it's equal to 1 after t greater than or equal to 0. All right. All right. So let's discretize this. So we know, I don't want to go all the way through it because we already did, but I want to remind us that we choose y1 of t to be equal to the actual output y of t. And we choose y2 of t, the second variable, to be the derivative of the first one, like that. All right, now discretizing this equation yields the first of the two equations that we need to solve to be able to solve this problem, right? Which basically is that y1 at the next time step is equal to delta t times y2 of t plus y1 at t. Okay, that's the first equation. And then we recognize that the second derivative here is the first derivative of the variable y2 of t, okay, plus 4 times y2 of t, right, by recognizing that the derivative of y is y2, and that we recognize that y is y1, so we say plus 100 y1. I'm going to call this x of t my input over here. All right. So we discretize the derivative, and we convert this into an algebraic equation, and we get that y2 of t plus delta t is going to be equal to x of t minus 4y2 of t minus 100 y1 of t times delta t equals, or not equals, but plus y2 of t, right? So this result here, I could have discretized. I knew the result from the previous slides. I've got two equations that I'm using to solve for y1 at the next time step. That's this one, and y2 at the next time step. Okay. All right. So those are my two equations, and I'm almost ready to go. So here's the summary, right? These are the two sets of equations that I basically end up with. All right. And so I need to go through and I need to solve those. Now, the critical thing is going to be that what I have to do is I have to choose my time step again. Just like with first order equations, I got to choose my time step. So that means I want to think a little bit about what the solution to this thing is going to be. All right. So first of all, we know that for any differential equation, the solution y of t, which remember is going to be the y1, that one's going to be the actual output, right? That's always going to be a particular solution, yp of t, plus a transient solution, yc of t, okay? And yp of t, the steady state solution, always looks like the input, okay? So in this case, we would say it's some constant b, I don't know what that is, times u of t, right? So it's some constant after t equal to 0. Because it's a second order equation, I know my answer, my transient response, is going to have two exponentials. So I'm going to say c1 e to the s1t plus c2 e to the s2t, like so. Okay, so that's my complete solution. It's going to have that form. I don't want to solve for all that stuff, but I do know that, right? And in this case, it's pretty easy for you to figure out what b is if you look at this, right? I'm not going to do it here, but you should challenge yourself maybe to see that it's going to be 1 over 100. All right, so it's going to be a constant. All right, and it's going to be a constant that's equal to 1 over 100. And I don't want to solve for C1 and C2. I don't want to go through all that, but I at least want to look at this thing and get a sense of what the exponential is going to look like, because I know that there's 4 ways this exponential can look, right? The transient response could have 4 different possibilities, right? One could be overdamped, right? One could be critically damped. One could be underdamped. And one could be what we called undamped, right? Oops, undamped. Right, so I had 4 choices for that thing, where I went from basically pure exponentials in the overdamped case to a pure sine wave in the undamped case. So I go from exponentials down to sine waves. All right, so I go from exponentials, and then eventually sine waves start to appear, and then I'm purely at sine waves. All right, so if I that's what this guy's going to be. I don't want to go through all the solution of it, but I do want to get some sense as to what it's going to be. So to get some sense of which one of these it is, and remember it matters, right? If it's overdamped, it's purely exponential. If it's undamped, it's purely sinusoidal. And so I got to have to solve that characteristic equation, which is s squared plus 4s plus 100 is equal to 0. And I got that by guessing that my answer was c e to the st. So I get that result. It's going to have 2 roots. Right. So to solve that, that's pretty easy to do with the quadratic formula. I don't want to do that. What I did was I basically plugged in to Matlab. I said if I had s squared plus 4s plus 100, I could convert that equation into 1, 4, 10, or sorry, 1, 4, 100. Basically, I put the 3 coefficients individually into this vector. And I use the roots command, and it tells me basically what are the values of s at which that equation s squared plus 4s plus 100 is equal to 0. So let me write the equal to 0 there. All right. And so I get that that's complex. And when I have complex roots, that tells me I am underdamped. Right. And I can go back, if you don't remember, I don't care about the specific formula. What I do care about is underdamped means that I have decaying cosines in my transient. So I basically have that result. You should remember that you have a decaying cosine in that particular case. I wouldn't challenge you to remember the formula. I just went back and wrote the formula down in this particular case. All right. So I have this decaying cosine term. And the decay is controlled by this e to the negative sigma t, where this real part is my sigma, and this imaginary part is my omega d. Okay. So in this particular instance, right, it looks like I have sort of 3 different features to think about when I'm choosing my time step. One is the whatever's going on with the steady state response, then whatever's going on with this decay, and then whatever's going on with this cosine form. Okay, so I have yp is one controller, right? Now yp we said was a constant, all right, and we said that constant was 1 over 100. Basically what that says is that at every value of t, yp is the same. So this guy really, in this particular case, has no impact on my decision. All right, so I'm not going to worry about that. Now, the e to the negative t over tau has some impact, and the cosine omega dt with an angle has some impact. Okay, so I got to think about what kind of matters here. All right, so one thing I want to look at with this real quick is I can see what my omega d is, right? My omega d is this 9.798 value, okay? Now the tau, I need to look at this and say, well, because it's e to the negative sigma t, that means that I got e to the negative t, well, sorry, e to the negative 2t, right? The real part of my roots was -2, so I have e to the negative 2t. So that basically tells me, just from looking at that expression, the tau needs to be 0.5, right? Because t over 0.5 would be t times 2, okay? So I have tau is 0.5, and t sub d, the period of this guy, would be 2 pi over omega d. That, if you compute it, is 0.6413 seconds. Okay, and remember the tau here is in seconds as well. Okay, all right, so I have that information, and now I need to use that information to choose my time step. All right, so let's go over here. All right, we said yp doesn't really have any effect on my time step. So let's look at the exponential over here, and let's look at the cosine term over here. So we said that exponentials basically decay in 5 tau. So I want to choose my delta t to be at least less than, or much, much less than 5 tau. We said our much, much less than sort of means at least a factor of 100 smaller than. All right, and then over here, I want to make sure if I want to see the full feature for the cosine, basically I want to see the full period of it. I need to make sure that my delta t, that's a terrible delta, that my delta t is much, much less than the period, t sub d. Okay, so basically what I'm saying is I got two constraints, right? I need to make sure that I satisfy both of those constraints. I need my delta t to be much, much less than 5 tau so that I see the full features of that decaying exponential. And I need to choose my time step to be much, much less than the period so I see the full details of a single period. All right, so we put the numbers in there. It says my delta t needs to be much, much less than 5 times 0.5 or 2.5 seconds. All right, so my delta t needs to be much, much less than 2.5 divided by 100. Or I need to make sure that my delta t needs to be much, much less than 0.6413. Okay. So one way to choose that, I mean, it's not much, much less than, right? At this point, by dividing by 100, I've made it much, much less than. So my delta t needs to be less than or equal to 2.5 divided by 100. Or my delta t needs to be less than or equal to, in this case, if you divide 0.6413 by 100, it would be 0.0064. All right. If I look at this, 2.5 divided by 100 would be what? 0.025 seconds. And in this case, it's 0.0064. If I look at those, it's the smallest of those two is the constraint that I must choose, okay? Because the smallest of those two will satisfy both of these two equations. So in this case, it looks like the smaller is the one coming from the period constraint. So I want to choose my delta t to be less than or equal to the period divided by 100. That's the period divided by 100. That's the constraint I'm going to choose. I can choose something smaller than that, but I really shouldn't choose anything bigger than that. Okay? All right. So it's time to code this up. So here's our code. First thing I do is I clear all, right? Then I bring in all the initial conditions and all that stuff. Here's my tau. Here's me choosing my delta t. Okay. So I chose my delta t to be t sub d over 100. And then notice here's kind of a key thing. I initialized all the variables that I'm going to need to store my result. So a couple of things here. X of t, my input was u of t. In other words, it's equal to 1 for t greater than or equal to 0. So what I did was I created a ones vector, right, that has the same size as my time vector. So that creates a vector of ones, okay? And notice my time vector goes from 0 in steps of delta t up to 8 tau. Now I decided to go to 8 tau because clearly what I want to be able to see in this particular case is I want to see the full transient response. And the length of the transient response is controlled by that decay. And so I said, well, it'll decay in at least 5 tau. So I want to see, the whole response. So let's say 8 tau. That goes a little bit past the end of what I would call the transient response. Okay. And then I need to solve for y1 and y2. So I initialize those guys as vectors of zeros. And then I have my for loop again, just as I did before, except now I'm solving for two things, right? I solve for y1 and y2. All right, so I solve for both of those. And then in the end, I just plot y1, because remember y1 is the actual output, y of t. Now I can plot the derivative of that as well and plot y2, but I don't need to. Now notice I also included in here a plot of the particular solution so I could see if things decay to the right value in steady state. I don't have to do that, but I did that just to check myself. All right, so what does that do? Well, I run that and I get something that looks like this. All right, so the red here is my yp. This is my y, which was in the vector y1. And I see, looks like it's decaying, in about 5 time constants to the transients over. I see the full decaying cosine. And I see that by the time I get to steady state, everything's kind of decayed. The transient's decayed enough that it looks like my total solution, my particular solution, have become the same. Now this, remember, was by a wise choice of delta t, which allowed me to see the tiniest of the features in the time domain. So I chose a delta t equal to t sub d over 100. Now, what happens if I make a bad choice? It's important to note that. So let's say I did this. So in this case, I chose delta t equal to tau over 10. All right, which should be, I think, 0.25 seconds. All right, 0.25 seconds. That 0.25 seconds means I'm only basically plotting that cosine. I'm only getting maybe 2 or 3 points in each period of that cosine. So what's that do? Well, it gives me a complete wrong result. And I know it's a wrong result. If I was looking at this, you should intuitively be able to see that that's wrong, because that surely is not a decaying exponential, right? That is an exponential that's growing. That's not even possible with a physical system like this, where I have all positive coefficients. If I have all positive coefficients, I better have decaying exponentials. There clearly is no decay in this result. So clearly something is wrong. So when I make a bad choice of my delta t, basically what that means is, back to the original equation, right? If I choose bad delta t's, then I'm basically not computing the derivatives correctly, and I'm getting a result that doesn't make any sense, okay? I'm getting a result that's growing instead of decaying, all right? So look for those kinds of clues to see if you've made a bad choice.